So if you were to feel the beaker in an exothermic reaction, what would it feel like?
Cold, cold. Smooth.
No,
Hot.
it would feel hot. Because let's recall on Friday you wrote this is the potential energy in kilojoules, and this is time. You remember it was a step down. Here were the reactants, here were the products. The difference in the energy was the energy exiting the system. So if you felt the beaker, which is part of the system or the surroundings? Surroundings. It would feel hot. Okay. All right, now, you're going to get this mixed up, so we're going to talk about this a number of times. When you do an enthalpy problem, remember enthalpy is equal, the change in enthalpy for a reaction is equal to the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. And then anybody remember that? So you find the enthalpy of the products, you put it here. You find the enthalpy of the reactants, you put it there. You subtract the two, that's the enthalpy of the reaction. What do you remember about elements? The value of the delta H of formation at standard conditions is 0. So anyway, if you found out that delta H for this reaction was a negative 1625 kilojoules, that sign signifies energy is exiting the system. Where is the exit to a chemical reaction? The product side. So you would say that the 1625 joules of energy is just like a product. This plus sign does not mean anything more than F2O3 and 1625 kilojoules of energy. Do you understand that? Perhaps. Okay. HBr, which is hydrobromic acid, plus cheese yields cheese squared. I don't think so. Here's an endothermic reaction. Yes, you do, is the answer to the question you want to ask me. All of it.
You have a picture?
What? Yes, the graph. It's not a picture, it's a graph. And yes, graphs are very important in science, especially chemistry.
day it'll drop down to about 0 degrees C. So it looks like we've got 7, and it's continuing to drop. The driving force for this reaction is the dissolving. The ammonium and nitrate ions are being surrounded by water, and it's going to a state of more disorder, as we say. It's making the reaction happen. But in the process, think of it as like an energy vortex. Heat from the outside, heat from the water are sucked in to make the reaction proceed. Oh, and very good, it keeps dropping at 5. There aren't too many of these reactions, so this is rather novel. I also give it the nickname of the cold pack reaction, because these first aid cold packs, these little plastic bags with an inside bag, are available at pharmacies. And what will happen is if somebody bumps themselves, like in the playground, somebody might come running over with one of these cold packs. What they do is snap it, and it's mixing the water on the inside with the ammonium nitrate, and it's spontaneously going cold, as demonstrated. Another little process loaded up here is just a simple combustion. I have some methanol, which is a 1-carbon alcohol, and I'm going to spray some on the counter and just go ahead and light it on fire. And flames are given off, a sign that we have heat, and I'll give personal testimony. It's warm. We have yellow, orange, blue flames here. It's combusting, heat's given off. That energy that's given off as heat came from chemical energy to begin with. Bonds are being broken, which costs energy, but then new bonds are being made and energy is being released. Let me go ahead and show you the processes up here on the board. The left side is the first reaction, and that is the cold pack reaction. The ammonium nitrate is a solid, and it's mixed with water and becomes ammonium nitrate aqueous. So these are two separate ions. NH4 plus is floating around, NO3 minus is floating around in the water. And at the beginning here, call it a baseline or the before enthalpy or heat. This is done at constant pressure. It is around here. And what's happening is it's sucking heat in from the environment, from the water and the air. The analogy might be something like your checking account. Your checking account starts here, then it's payday and a deposit is made. Ooh, that's nice. We increase the heat of the system, or the enthalpy, the heat at constant pressure. The time axis is simply just showing before and after. I have an arrow here going heat is taken in, so the energy of the system rises. Endothermic, or entering heat, heat enters the system. On the right side is that combustion of the alcohol. CH3OH is methanol. It burns in oxygen in the environment, and then we produce carbon dioxide and water. We start off with some high energy bonds, and then we end up with basically waste products, carbon dioxide and water. When you exhale, carbon dioxide and water come out. You extinguish candles with this. We use these in fire extinguishers, very low energy molecules. We start off high, we end down low. There's a little bit of an activation energy at the beginning, that hump that we have to get down over. Heat is given off in this process. Exiting heat, exothermic. What I'd like you to do is think about the delta H values for these two. One is going to be positive, one is going to be negative. Which one do you think is positive? Which one's negative? Have a look at the plots. See what's happening to the energy of the system. I wrote down.
So what do you think? Which one's positive and which one's negative?
The left one's positive, the right
The
one's
left
negative.
one is positive because
It goes up.
it goes up. And then the next one is
Negative.
Just goes down.
Then our endothermic is positive. We have an increase in enthalpy. You can see the before and after case. And our exothermic process starts off high, goes down low, so there's a loss of system energy or system heat. So that's a nice little couple of examples of endo and exothermic. I do want to point out the activation energies, which are the energies required for the reactions to proceed. The activation energy for this, the exothermic process, is just a little hump. These molecules need a little bit of energy. Think of it as the match at the beginning. Get over the hump, and then it's all downhill from here. We call it PA, the activation energy. Now, many people will look at this and they might be thinking, hey, the activation energy is that little hump there, but it's not. The activation energy for an endothermic process would be the entire peak, the whole thing. And that's because it's being based on the definition of the activation energy. The energy required for the reaction to proceed. So we're starting here. If we give it just a little bit of energy,
So if you were to look at this, the energy of the reactants would be what?
20.
Would be 20 kilojoules. The energy of the products would be about 80 kilojoules. What would the energy of the reaction be? We would call that the heat of reaction, and that would be still the products minus the reactants, which in this case would be 80 minus 20, and that would be 60 kilojoules per mole. Is that a positive number?
Yes.
Yes, it is. All right, what would be the activation energy here? EA
80.
would be from here to here. 100 minus 20 would be 80 kilojoules. What would be the energy of the activated complex?
80.
All the way down here.
100.
100. The activated complex would be 100 kilojoules. Try to paraphrase. Try to write only what you think is important. Here, the total chemical PE, potential energy. So PE of the reactants is less than the PE of the products. More energy is needed to break the bonds in the reactants. So the energy for the reactants to break is greater than the energy when the products are formed. So energy must go in, endo, kind of the same. If you felt an endothermic reaction, what would it feel like? You felt the beaker in which an endothermic reaction was taking place, it would feel cold. Energy from the environment would be going into the reaction.
Is that kind of grapes?
What?
Is that kind of grapes?
Nope. All right, in an endothermic reaction, when you did your enthalpy of the reaction equals the products minus the reactants. For an endothermic reaction, that would be a positive number. In this case, the number was 27. you can either put a plus sign, or you could put it in the reaction, and you put it where it belongs. It belongs right here because energy entered into it. So heat is written on the reactant side because it enters the system. You do not need to write this down. The skills you should have at this point is you should be able to look at and determine whether there's an exothermic or endothermic reaction occurring by looking at the graph. If it's a step down, it is exo or endo. Exo. If it's a step up, it's endothermic. You can calculate using a table the delta H of a reaction. If it's positive, is it exo or endo? Endo. And if it's endo, is heat on the reactant side or the product side?
The products.
Reactant.
Reactant. Got a little work to do here. You can observe a chemical reaction, like tomorrow you will be doing, and feel the change in temperature. If it's exothermic, it will feel hot or cold. Hot. Okay. All right, you need to know whether a chemical reaction has occurred, and you have been taught the evidence of a chemical reaction. This is one piece of evidence that a chemical reaction has occurred. What is it? A gas formed. This would be change in temperature, and we call one an exothermic, where heat is exiting the system, and the other one we call endothermic, where heat enters the system. Okay, what is this a sign of?
New solid form.
A new solid formed. This one is a,
Color change.
yep, a color change. And this one is
Smells.
odor. Okay. Now, one thing you have to keep in mind in all chemical reactions is you cannot create or destroy matter. And all matter just change forms. Therefore, in a chemical reaction, this is what you're writing down. The number of atoms, the mass, and the charge must be conserved. All right, if you start out with 2 diatomic A's and 2 diatomic B's, I don't care what position they have in their products, you still have to have the 2 A's and the 2 B's. Otherwise, you break the laws of conservation of matter, and you can't do that. Okay. Look at how that thing's bouncing around. That is not me. Okay, ladies and gentlemen, I would like you to, on your worksheet, find this problem. Yes. Omar, thank you. Did you find it? Okay. Here are the directions for this. Oh, look at that. For this worksheet. It says, calculate the change in enthalpy of the reaction for all of these reactions. Determine if it is endothermic or exothermic. How are you going to do that? By positive or negative. If it's negative, it is exothermic, and label that in the blank to the left. And you would write the amount of energy, the number of kilojoules, on the left or the right, depending if it's exothermic or endothermic. If it's an endothermic reaction, would you write the amount of energy on the left side or the right side? Left side. And when you're done showing your work, box your answer. Okay, so we know that to find the change in enthalpy of the reaction, you have to take the enthalpy of all the products and then subtract the enthalpy of all the reactants. And we recall these are the reactants, and then these are the products. So let's start doing that, the products. So we have 2 waters, that's in the gaseous state. So we have 2 waters. These values are only for 1. We have 2, so we have to multiply any value in here times 2. 2 times negative 241.8. That takes care of our 2 waters, plus 2 SO2 gases, negative 296.8. From that, I'm going to subtract the values for the reactants. 2 of the H2S in the gaseous state, which is negative 20.63, plus 3 of the oxygens, which is 0. So let's consolidate our terms right here. 2 times 248 is, a negative 241.8 is negative 483.6. To that, I have to add 2 times minus 296.8, which is negative 593.6. Then 3 times 0 is
0.
Thank you. 2 times negative 20.63 is negative 41.26. If I add these 2 together and then subtract this, I come up with an answer that is negative 1038.94 kilojoules per mole. Is this exothermic or endothermic? Exothermic. If it is exothermic, does this value belong as a reactant or a product?
Product.
Do I include the negative sign when I put it as a product? No. So you would write 1038.94 kilojoules. You are now ready to go.